All right, we need an example where we have to calculate the radius of curvature at an instant, and here it is. Anytime we've got y as a function of x, pretty good sign that we don't have a radius of curvature that's constant. Therefore, we're going to have to find an instantaneous radius of curvature at just a particular moment. So on this one, we've got a train going from A to B. You can see how it's got a curve. But that curve is defined as this rather than by some constant radius. They give us its tangential acceleration, so that's nice. And we want to find the magnitude of the total acceleration when it reaches point B. And they're telling us the path that it's gone on is 412 meters long. Interesting. So that's the path along the curve. In the x direction, it's moved 400 meters. We could plug that in and find how far it's gone in the y. That might be useful later. But what we really need is the normal component of the acceleration, which is going to require us to have what? V squared over rho. We'll need an instantaneous rho. Okay. So if we're going to find V squared over rho, we need to have a V. They didn't give us a V at point B, which is what we're looking for, right? We have a V at point A. We also have a constant rate of change in the velocity. Ooh, constant acceleration. I like the sound of that. Um, so let's see what we can do. I'm gonna swap screens here. We'll just bring this over there like that. So what we need to do is we're gonna say, all right, if I've got a constant acceleration at of negative 0.25, right? And then what they gave us there, meters per second squared. Then if I'm going from point A to point B over the course of 412 meters, then my final position is 412.5. Is that what we said? Nope, just 412 meters. My S initial could be 0. My acceleration is that. So I'm thinking S equals S naught plus V naught T plus 1/2 AT squared. That's looking like a pretty valid equation for this situation. Do we know our V naught? Sure. If we're going from A to B, what would our initial be? It says we pass A going 30 meters per second. So there's 30 meters per second. We've got T. Do we have a T? We don't have a T. So we need to find a T. Interesting. So how about let's look at a different equation. What about the one that says V equals V initial plus AT? Could we get T out of that? I think so. Right? We could get V, and this would be the V at point B, right? We could even replace this with VA and SA if we wanted. But V at B is going to be the initial V, which was 30 meters per second, minus 0.25 T. Heck yeah. Now we've got it in the bag. We could say 30, um, well, kind of. We've got two equations with the same unknowns in it. So let's plug into this one. Let's say 412 equals 0 plus 30 T plus 1/2 times negative 0.25 T squared. Kind of ran out of room there. Now we've got T and V. We could solve this one for T, and we should get T equals 14.62 seconds. We could plug that back into V, and we will have VB is 26.35 meters per second. Pretty sweet. We got the V that we needed. So let's remind ourselves what we were doing there. We did our constant acceleration equations because we had constant AT acceleration, but we needed AN, and AN we know is V squared divided by rho. So we've got this halfway taken care of. Now we just need a rho, but it is not constant this time. So we need to come up with an instantaneous rho, which was that somewhat unwieldy equation that we had a minute ago. All that raised to the 3/2 power, all divided by the absolute value of the second derivative in terms of x. So as long as we can come up with those two derivatives, plug them in, we should be able to get a instantaneous rho. So let's come up with dy dx. dy dx is going to be d dx of that function that they gave us for the train, 200e raised to the x over 1,000. Oops, lost our screen there. There we go. So the derivative of 200e to the x over 1,000. Okay, so because we've got some chain rule going on in here, I'm going to pull the 200 out. That's going to be 200. This 1 over 1,000 is going to need to be multiplied by everything. So there's 1 over 1,000. E to the x over 1,000. Right? Just a little chain rule there because this has the x inside it. So I needed to multiply the whole thing by the derivative of that function. So in other words, 0.2 e to the x over 1,000. That is our derivative there. We need to do it one more time. The second derivative would be the derivative of that, which would just be 0.2, and it would just be 0.2 e to the same thing, right? But there's a function inside of that, so we need to multiply it by 1 over 1,000, the derivative of the inside function there. So again, we're dividing that by 1,000, e to the x over 1,000. Nice little chain rule there. So that's going to be a very small number. There's our second derivative. Let's plug in x's and get what we need there. So this one, when we plug in x, what x are we going to plug in? At that instant, what is x at b? 400 meters. You see that? So let's plug in 400 meters. So this would be 0.2 e to the 400 over 1,000. That will give us, I didn't actually calculate those individually, but whatever that comes out to, we'll just plug them in at the end. We could also plug in 0.0002 e to the 400 over 1,000. We'll come up with a number there. I'm going to plug it all in and do it in one instant and find our rho to be 3809 meters. Ooh, there's an M. That's our instantaneous rho at that moment. So 3809, we need v squared over rho. So AN equals the velocity that we came up with earlier, 26.35 meters per second. That gets squared on top, divided by 3809 meters below. Our units work out nicely there. 0.183 meters per second squared. And we're just about there. The final magnitude is just square root of the sum of the squares. 0.183 squared plus negative 0.25 squared, the given AT. And finally, we've got it in the bag, 0.309 Meters per second squared. That's our final answer for that one. So that's a good little problem there where we've got no constant radius. We had to come up with an instantaneous radius.